Record.
Recording in progress.
Okay, so it's Tuesday, day 6. So last time we spoke about what spectral sequences are. I gave a little bit of some motivation, and then there was some terminology that I talked about. I'll just continue from there, and we can just keep moving. Okay, so just before, okay, maybe I should just say something just as a refresher, like, okay, spectral sequences look like these. Each red dot represents, okay, so in here, the E0 star star or asterisk asterisk, each node represents one of the E0 PQ, where P and Q take on integers. At least in these pictures, they're in the first quadrants. And so here I've drawn pictures for the maps between each of the modules appearing in each sheet of the spectral sequence. And so the punchline was, okay, to move from sheet to sheet, you only move upwards in the sheet count, and you do that by taking cohomology. So going from E0 to E1, take cohomology at each node, replace that node with whatever you get. That's your E1, so on and so forth. And then as you do this, the differentials change in some prescribed pattern. Basically, every time you take cohomology, the new differential points one more node to the right and one more node down. So it starts by pointing up, then right, then doing this knight chess move or whatever, and then longer and more down, whatever. And so I said something like, okay, for first quadrant or just more generally bounded spectral sequences, eventually these maps all become zero-morphisms of some kind. And so we talked about stability, or the stabilization of each of the nodes. Okay, so now back to where we are. Now the most important concept, which is convergence of spectral sequence. I'll just give the most basic definition here. So this is for bounded spectral sequences. So a bounded, okay, hold on. I should write this up here. A bounded spectral sequence converges to H asterisk if there exists, if there is a finite filtration of Hn for each n. So Hn for each n, this will look like the following. So I'll have 0 down here. Of course, it's also like before, a decreasing filtration. So 0, okay, maybe I put equals ft Hn all the way down to, oops, fs Hn. Here, the t and the s depend on n, but they're finite. So the filtration does not extend in either direction. Yes.
So Hn is just some quotient complex?
Or
sorry,
H star is some graded, or sorry. Yeah, it's some graded ring, okay. Graded module. I mean, think cohomology ring. Yeah, that's supposed to be what it's modeling. So.
Okay.
Yeah. So. Yeah, each Hn you should think is just like the cohomology, the nth cohomology of some space or something, or whatever, or of some cochain complex, and we've assembled them into this graded ring. Or yeah, graded ring. Yeah. Okay. And so there's a finite filtration of Hn for each n. So each of the graded pieces of H star, H asterisk, has a filtration like this, and we get the following isomorphisms. So because we're in a bounded spectral sequence, we have this stabilization condition up here. And so we can say that E infinity PQ we say this, so we say that convergence set means that this isomorphism holds, that we have FP HP plus Q modulo FP plus 1 HP plus Q. And so, okay, you should think P plus Q is equal to N throughout. That's the sort of feeling that we should have. Okay, but this is the definition of what it means for a spectral sequence to converge to a graded ring. Okay. Here is an example for first quadrant spectral sequences. How am I on time? 10 minutes. Okay, good. So example, the first quadrant spectral sequence. So write the 1, 2, 3, 4, 5, 2, 3, 4, 5. Here's the first quadrant. I'll draw in some of the nodes. Oops. Like this. Maybe one more for good measure. Okay. Let's say this is the E infinity page. Okay. You may object that, like, so okay, the notion of stabilization, it could be at a different page for a particular P and Q. The particular R that it takes to stabilize, it may be different for each P and Q. So you may object that, like, why am I drawing them all in the same sheet? We won't, well, okay, the reason is, at least in this picture, for the first quadrant spectral sequence, is that at least for a fixed diagonal, which is what we're going to be focusing on, we're going to look at just a fixed diagonal like this. For a fixed diagonal, you can pick an R big enough so that all of them become stable. So that's why I'm writing this E infinity page. Okay. Right, this is the P axis, this is the Q axis. I might forget to write P and Q in future pictures. So, okay. Oh, and the notation, some notation is that in convergence, we also write that ERPQ, we write this double arrow to mean converges to HN? No, HP plus Q. Yeah, okay. P plus Q is always N for me, just because I'm always thinking about diagonals. Okay, so that's the notation. So, okay, in here, if this, so EA, whatever this A is, I mean, it starts at some page, doesn't matter. If EAPQ converges to HP plus Q, then we have the following. There's a filtration, that looks like this. So 0 to F. Now, N plus 1 HN. So, okay, here, P plus Q is equal to N. Let's just fix that. No, I can just say for all N. Okay, so Fn plus 1 Hn, that's contained in Fn Hn, all the way down to F0 Hn, which is just Hn. Right, so this, how many terms are in this? So there's it's from 0 to n plus 1. So how do I count? There should be n plus 1 terms in this filtration, including the top one, which is just Hn, right? So then we get the following isomorphisms by the definition of convergence. So E infinity PQ is isomorphic to, so FP HP plus Q mod FP plus 1 HP plus Q. Right. I mean, this, I just repeated the same thing, but so the point is that each of these, So in this picture, I picked what, n equals 3. So we should have a 4-term filtration. So going from F4H4 all the way down to, sorry, H3 down to just H3. And then you can just write out each of the isomorphisms for those. And so those are the associated gradients of H3, right? Each of these E infinity PQs, these are these quotients. And so up to extension, you sort of assemble these E infinity pieces together and you can recover H3. Okay, so maybe you can, yeah, maybe I just leave it like this. Maybe I'll write down a few notable isomorphisms. So, I mean, so E0 and infinity, that one is isomorphic. Your question?
Didn't you say last lecture that you need more than just knowing the associated gradients to construct the original?
Yeah, you do. So, I mean, this is up to extension.
Okay.
Up to extension. You know a little bit more about H3 than you did before if you could get all the information you need to show convergence.
Okay.
Yeah. This is all like formal so far, more or less. But yes, up to extension. That's the sort of caveat. But maybe you're working over a field, in which case, great. Just direct sum up. Okay, so for a particular n, so if I put 0 n here, then I'll get F0 hn mod F1 hn, but that's just hn mod F1 hn. And then if I flip it, so okay, and 0 infinity, this one is isomorphic to, now it's the last quotient, or the, okay, I don't know how to order these, but this one is just going to be Fn hn mod, oh, my bad, this is a typo. I should have equal here. Yeah. So maybe I misspoke. Yeah, okay. And then here's Fn plus 1 hn, but this thing is 0, so this is just Fn hn. So, okay, this term be, I'll do it in gold. So this one here, this one is, so P equals N, that's, and Q equals 0. So that's this one down here. And then this one here is this one up here. So that's just what it looks like for a picture. You can imagine where the rest of the E infinity terms will lie. Okay. So, okay, more terminology. So something that is apparently very typical. I don't have a lot of experience with spectral sequences, but in my reading, it says that this is the case. It is apparently typical that spectral sequences, so they do what is called collapse. They collapse at a certain page. And what does that mean? So, okay, a spectral sequence collapses at the page ER if there is only one row or column, only one, I should say, non-zero row or column. Okay, maybe, okay, at most. You can wiggle your finger, fine. If there's at most one non-zero row or column in this page, and it's row or column, not both. I just mean like literally one like line. So maybe X or, okay, whatever. So okay, what is the upshot when a spectral sequence collapses? So okay, if the spectral sequence also happens to converge to HN, so okay, if we also have that EA PQ converges to HN, or okay, P plus Q, whatever. P plus Q or N, maybe I will mess that up, but it's like the same, don't worry about it. Okay, so if this happens and it collapses, the spectral sequence, oops. Something nice happens, you can just read off the homology. And the reason is because, okay, what will happen? In each diagonal, there will only ever be at most one non-zero node, right, in a diagonal, which means the filtration that you get will have at most one non-zero thing in it, which is to say the HN, right? And so that E infinity term is going to be isomorphic to the HN, which is all to say that you can just read off the cohomology directly from that collapsed page. You can read off H star from the E infinity terms. So that is to say, HN is so it collapses, okay, so it's at ER, right? So then it's this. Oh, okay, P plus Q and whatever. Yeah. So that's convenient, and apparently this happens frequently. I don't know. I mean, I've seen it in the proofs that come up. Okay. So now, okay, maybe I've spoken a bit too much about terminology, and it would be much appreciated if I just did some calculations with like toy examples, probably, of just like really simple formal spectral sequences. Okay. How am I on time? 22. I'll have a sip of water. So this first example is going to be the 2-column example. So suppose we had a spectral sequence starting from page 2. And it converges to H star. Where, okay, I said it was 2 columns, so I specified the E2 nodes. So where E2PQ is equal to 0 unless P is equal to 0 or 1, right? 2 columns. So, okay, what does it look like? So this is E2. The E2 page looks kind of like this. I'm just going to not worry about where the Q equals 0 line is, or I mean the P equals, wait, yeah, Q equals 0 line. I'll just draw the vertical parts. Okay, so here are some nodes. Maybe here. Oh, I guess I need to make this one longer. Yeah, so it looks like this. And so, right, this is the E2 page. So what are the differentials? They're the chess knight moves. So what do they look like for the red nodes on the left? Well, they go out to nowhere, to 0 node, to 0 modules. So I'm not going to draw those in. And then the same thing with the ones on the right. So every morphism here is a 0 morphism. And what does that tell us? It stabilizes. This is done. This is actually the E infinity page for all of the nodes. Or so you can say this is infinity. So okay, all the maps are 0. This means all terms stabilize, which is then to say, okay, i.e. E2 is E infinity star star. And I mean this both uniformly and pointwise, whatever. Okay. So for each n, we also have this convergence condition, right? For each n, we have filtrations of hn that are length 2, right? Because each diagonal is going to have 2 possibly non-zero nodes in it. So the filtrations will reflect that. I mean, you could have like a bigger one, I guess, but I mean, you get a bunch of zeros and stuff. So for each n, we get filtrations that look like this. So we have 0 that could be equal. Okay, so 0 equal f2 hn. I think I'm just not going to write that one in. I'm just going to write 0 contained in f1 hn contained in f0 hn, which is just hn. Right. So for each n, we get this filtration of some kind. And so now what does the convergence result or definition say? It says, okay, that says E infinity, which is just E2, right? E2, okay, well, it's PQ, but maybe I should pick my P correctly. So either my P is 0 or 1, so I'll start with 0. So 0, and then my Q can be, well, I guess anything, right? So I'll do 0n, maybe, right? Because I'm thinking P plus Q equals n anyway, so 0n. So E0n2, this thing, right, by definition is F0 hn mod F1 hn, which is just hn mod 1 hn. And then the other one, which is, which is E, well, now my P can be 1, but then I have to have n minus 1 here. And then that's 2. This one is just going to be F1 hn, right? So then for each n, I get a short exact sequence. That's 0 goes to, so this one should be the small chunk, which is E2. I mean, F1 hn, which is E2 1 n minus 1. That's contained in hn. And that surjects to this quotient, which is just the hn mod F1 hn, but that's just E2, or sorry, E20n, right? So for each n, I get a short exact. So this is what I meant by, like, this is the simplest, I guess, example of that extension thing I was talking about. You have to put together the E infinity terms together to get the hn. Okay. So maybe next, we should do the next natural example or variation of this first example, which is the two rows example. This one's a little different. Okay, so 2 rows. It's 4:30. So I will dispense with writing the words down. I'll just say, okay, E2 PQ equals 0 unless now Q is equal to 0 or 1. And then we also have the convergence. So E2 PQ converges to HP plus Q. Okay. So now I draw the picture for the E2 page. So this is, so I'm not going to draw the P equals 0 line. I'll just draw something like this. And then I'll put in some of the nodes. So here, maybe like this is okay. Okay. And so now, unlike the last one, some maps, exactly half of the maps that I care about aren't necessarily zero maps, right? So the horseshoes or the night move maps look like this. And so those could be non-zero. So at this stage, I don't have any stability. So what should I do? I should look to the next page and see what happens. So, okay, let's take homology and then go to the E3 page. And I'm lazy, so I'll just copy paste the picture. Okay. But now the maps are different, right? Now the maps, oh dear, so 3 across, 2 down, right? So I mean, whatever that is, it's like gone for every node. And I mean, I didn't even look at the bottom row to begin with. Those always went to zero modules anyway, so whatever. So, okay. Now we've stabilized. If I continue to take another page, nothing would change. Great. So this is the infinity page for all the nodes, which is nice. Okay, so just like in the last one, last example, you can form these short exact sequences. So maybe I'll do that very quickly. No, I got time, maybe. I'll try to elaborate as best I can or as succinctly as I can for this sort of example. If you don't believe me, it's a good exercise to fill in whatever you don't believe, right? Okay, so we can just look at a random diagonal like this. Say this is I mean, whatever n is, maybe n is here. So we have, we get filtrations of length 2, right? We get the same ones, right? It's a 0 in F1 HN, in F0 HN, which is just HN, just like last time, because I only have two possibly non-zero nodes. So then, okay, stabilization tells me E3 and 0, just like before. I mean, I'm just going to write down what the result is, F1 H1, and then E3. So now my Q can be 1, but now my P has to be n minus 1. So n minus 1, 1. That's going to be HN mod F1 H1 or n. Oops. Yeah, n. Did I make that typo earlier? I hope not. It looks okay. I'll leave it. Whatever. Okay, so then you get these. So let me move this somewhere convenient, somewhere nice, maybe here. Okay. And maybe I should, well, okay, I know this because I worked out this example in full, but it will be convenient to write down in terms of the E2s what the E3 terms are. So literally taking cohomology, what do we get for the E3 n0 and the E3 n minus 1, 1? So, okay, by definition of how spectral sequences are arranged, the E3 n0, this one is, well, it's the kernel of a 0 map mod the image of a D2 map. I'm going to not worry about the actual indexing here. And so this is to say, okay, maybe I should do this vertically, maybe. This is okay, the kernel of a 0 map out of one of the E2s is just E2. And here it's going to be N0, right? And then the image of D2, it's the image of a D2 map going into an EN0. Now, N0 means, oh, did I mess this up? Yeah. What am I doing? I think I looked at the wrong. Yeah, no. So far I'm correct. It's a D2 map going into N0, which is one of these. So it could be non-zero. So I'm just going to leave that as it is. Okay, what about this one? This one is kernel of D2. So, okay, and then image of another D2. But actually this one is a zero map, right? So n minus 1, 1, that's the one on the first row, right? The top row. So a map going into it on the E2 page is a zero morphism, so image 0 on the bottom. And then a map out of it is D2, and that could have a kernel. And so that's just kernel D2, right? Great. So, okay, this will be convenient for later. So I'm actually just going to copy paste this, or I might have room to do this on this. No, I'll just do it on the next page. Okay, so I'll copy paste this. And I'll make it like really small here. Maybe hopefully it's still like legible or something. It's just for reference. So, okay, at the E3 page, we get these short exact sequences, just like in the last one. You can do 0, E3. So E3 N0 was F1 HN. So this one is N0, and that goes into HN. And then we surject onto E3 N minus 1, 1, and then goes to 0. Okay, but one other thing you can do is you can make a long exact sequence using some of the E2 terms. So this is what I mean by like, it's sort of this idea of gluing together in some sense, or stitching together a bunch of long exact sequences and producing a bunch of maps. And now there's a bunch of data that's sort of tied together in a neat way, possibly. And so this is one example of something like this that can happen. So, okay, maybe I want to involve the E2 terms. One way I can do this is, okay, so E2, so what index should I use here? Well, okay, maybe I should look at over here. So E3 N0 is a quotient of E2 N0. So, okay, there's a surjection that I can do like this. Okay, great. Okay, and then over here, kernel D2, well, okay, this is kernel D2 out of the E2 N minus 1 page. So this kernel D2 is contained in, this is contained in E2 N minus 1, 1, right? So if E3 N minus 1, 1 is isomorphic to this kernel and is contained in this E2 term, I can make this injection, right? E2 N minus 1, 1. I can do that, right? Yeah. So then I'm going to make this, I'm going to write down a sequence, and I will just simply assert that it's exact. And it's actually not even that hard to show that it's exact. So, I mean, once you have this, you can't help yourself but write down the D2 map here, right? So, and then the same thing back here. So we might as well do that and just sort of compose this map and compose this map and just deal with E2 terms everywhere. So what does that look like? So I'll just write ... goes into, okay. And so, I mean, this is always like a horrible headache with indices, right? So E n minus 2, 1, sub 2, that maps by D2 into E n0, 2, which maps into Hn. That's that map above the surjection and the, oh, here, oops, this should be n0, my bad. Hn here, and then Hn goes to E2 n minus 1, 1, which by the D2 map, by the differential, it goes to, where should it go? well, I have my notes. So this is en plus 1, 0, 2, so on and so forth. And I claim this is a long exact sequence. Why is that? I mean, you can just check immediately. So the exactness here in the short exact sequence automatically gives me exactness here. So that's good. So exact here, good. That's due to exactness here. What about over? Oh, I should have done that in green. Okay, I'll just do this then. What about over here? So, oh, no, sorry. I want to do it over here. Oh no, I was matching my notes. Okay, fine. I'm just picky about colors. So, okay, how about over here? So I need to look at the kernel of the D2 map going out of En minus 1, 1. So I have, okay, kernel D2, and I have to compare it against the image of the map Hn to, well, okay, it's, oops, so En minus 1, 1, 2, but that map is just this, right? The composition of these two. But the image of this composite green arrow that I've drawn up here is just the image of the first blue arrow, right? Because the second one is an injection, it's not really doing anything. It's not going to change the image. It's just yeah, it's just embedding in something bigger. So, okay, exact, fine. And then you can play a similar game over here. And then over here, right? It's the kernel of this thing up here, which is again just the kernel of the surjection, right? Because the blue arrow is an injection. It wouldn't change the kernel. So it's just the kernel of that red surjection, top left. So, okay, dot, dot, dot. Yeah, it's exact. So it's not bad. And then, I mean, this is the same anywhere, same arguments wherever you look in this long exact sequence. So this is a fun, cheeky example, I guess. Okay. I spent too long on that example. We're not gonna finish. Oh well. At least we did it though. That's fine. I mean, this is why I scheduled for 2 weeks, so that we can just chat. Okay. So yesterday, yeah, it was yesterday. Feels like so long ago. Yesterday, I was talking about this kind of vague motivation for spectral sequences out of stitching a bunch of long exact sequences together. I'm going to write down the theorem now that we have all the language. I'm going to write down the theorem that sort of summarizes what I meant by that. So this is the theorem involving, so it's about the cohomological spectral sequence associated to or for associated to a filtration and a filtration of a chain complex. Okay, so the theorem is, so let X bullet be a, okay, co-chain complex, whatever. So X is a cochain complex with a decreasing, and so I'm going to use a word here that I might not have defined yet, bounded. I'll just clarify this in a moment. Decreasing bounded filtration. It looks like this. So I'll have dot, dot, dot contained symbol A2 bullet, contain A1 bullet, and then A0 bullet, which is just X bullet, right? And so bounded means, so if I pick an n, if you pick an n and you place each of the bullets with an n in this filtration, you actually get a finite filtration. So pointwise is finite, let's say. pointwise finite filtration is, I guess, how I like to think of it. For bullet equals n, get a finite filtration. And so, of course, the actual length can depend on n, whatever. So then there is a spectral sequence. And okay, it starts on page 1. Whoa. With, okay, so I write down the E1 terms. So E1 PQ, that's going to be HP plus Q, so the cohomology of this quotient complex. So AP mod A bullet P plus 1. And this thing actually will converge to HP plus Q of X bullet. So this is what I was hinting at yesterday. So that somehow you can use these quotients and the long exact sequences that come from the short exact sequences. You stitch them together in a funny way, spin out all these random maps. You can just do this with a spectral sequence in a much more concise, I guess, way. Okay, I can make a remark here maybe that you can actually start this on page 0. You have some choices here, I guess. You can actually do so 0, and what you can do is so E0 PQ. You can just define it to be AP P plus Q mod AP plus 1 P plus Q. Hopefully I got the indices right. Yeah. Yeah, so like, okay, I mean, does this check out if I take the cohomology of the E0? Do I get the E1? Yeah, you do. I mean, that's just, yeah. Okay. So you can do that if you like. Okay. And yeah, I should write out then. So because of this bounded filtration thing, you actually get like a stabilization. So bounded filtration, what happens is I get the stabilization. So E infinity PQ, you actually get like before. It'll just be FP HP plus Q of, so what? Oh, okay, yeah, right. It should be X bullet here, right? It's a so there's a filtration of the HN of X bullet, and then the E infinity terms meet these quotients. So FP plus 1, HP plus Q, X bullet. Okay. Yeah. Okay. 447. Okay. So here's an interesting idea now that we have some more language. So interesting idea. So in the previous theorem, it looks like we could have just used any bounded filtration of X bullet. So in the previous theorem, we choose, so we choose filtration. We choose a bounded filtration for X bullet, and then we spin out this spectral sequence. So everything involved in the spectral sequence depends on this choice of the filtration. So now you may wonder, like, okay, maybe depending on the situation, maybe there's a convenient filtration that I'd like to use. Maybe, maybe there are particular ones that make the spectral sequence collapse, right? Maybe if I have two different filtrations, maybe I just look at both spectral sequences that I get from them, and maybe they inform me of something interesting about the other one. I mean, I'm being super vague here, but like the point is you should consider what happens if I use different filtrations. So that is a theme in some of the results. maybe a lot. I don't know how many. I'm still new to this, so I don't know how many, but this is a very important idea that comes up. And so now, maybe, do I want to do this on this page? So, okay, I should just summarize. So consider using different filtrations of X bullet. And usually what people like to say is that you play the spectral sequences against each other. And maybe something clever will pop out, something curious. Okay. So we'll investigate this idea in the context of double complexes. So we're back, like IKEA furniture, no extra pieces. So return to double complexes. So recall for a double complex C bullet, we can form the total complex. So tote, and you could use product or direct sum, C bullet. Let's just write tote C bullet from now on, because I'm lazy. I mean, whatever. It just depends on the complex we have, whatever it is. And so there are two filtrations that we can, I should say, there are two interesting filtrations we can choose for the total complex. Two interesting, oops. For code C bullet. Okay. So the first one is by columns. So, okay, I'm going to write something down, which is just the pieces of the filtration. So it's going to be, so I'm going to write it down and then I'll draw the picture. So this FK, so I write this I behind it because I'm going to do, the next one is by rows and I want to distinguish, the notation will look very similar. So I FK, so okay, I'm just going to say FK tote C. This is the total complex of, so I'm going to write happy face here. And so happy face, oops. Happy face is this new double complex that I get from the old double complex. So now I write down a cross. I'll try to make this picture succinct. So maybe, I mean, so we can have a double complex like this. 1, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this so far is just C bullet, right? But I'm going to filter by column. So I have this K here. So K is over here. So I'm just gonna draw like a random K, maybe K is over here. Okay. The P equals K column. And what I'll do is to the left, I'm gonna set everything to 0. Okay. So I'm just chopping off. I'm just getting rid of everything to the left of K. And then whatever's left, I take the total complex of that to get this piece, FK tote C. So so I highlight what the pieces are in the total complex. They're just these types of things. So the picture is kind of awful, but okay, you get the idea, right? So that is to say, so maybe I should write in symbols. So FK tote C bullet. So the nth piece in this new complex is, again, it's P plus Q equals N, but now P has to be strictly greater than, or it's not strictly, it's bigger than or equal to K, right? since everything to the left of it is going to be 0. And this is CPQ. Okay, so I've filtered. Okay, so I mean, there's a lot going on here, right? I have a lot of complexes, so I should be very slow when I say these things out loud. So I filtered this new complex. So, okay, sorry, I filtered the old complex, which is the old complex. What I mean by that is I filtered the total complex of C bullet by making these new total complexes, which are just, well, I mean, visually, it just looks like slices, like growing slices of the double complex and making the total complex out of that. I don't even know what I said. That was horrible. But the picture, you should use the picture. So we filtered the total complex is the point. And so now we get a spectral sequence involving this filtration, just like before, but now X bullet is C bullet, right? So I get spectral sequence. So I get the spectral sequence. And you can start at the first page, you can start at the 0th page, I think, in the future. I probably won't get to this today. Oh dear. Yeah. Yeah, I won't get to this today, but I should just write this down and end here. So yeah, so the spectral sequence we get, at least for the first page, you could do 0. Well, I will do 0 later, but I mean, it's the same thing, doesn't matter. So I specify, so these, so r bigger than or equal to 1 with E1 PQ, this is just going to be, oh, okay, actually I do start with 0 in this. So E0 PQ is just going to be this quotient, just like up here in the red. I'm just going to do this, but cast, I just use, I use the pieces here. So this is going to look awful, but it's this, so FP toad C bullet sub P plus Q, and then mod out by FP plus 1 toad C, and then sub P plus Q here. And then the DU0 maps are the ones that are actually they just come from the DV in C bullet. So then you can write down that, so the E1 modules are just going to be, so you take homology, right? You get the vertical homology at Q of the complex CP bullet. And then you can check the D1 come from DH from the double complex. Okay. And then I've got like 2 minutes maybe. You can do the second one by rows. Am I going to be able to write this down quickly enough? Okay, I might go a couple minutes over. I hope that's okay. I don't like going over if I can avoid it, but it's not good to stop in the middle like this due to symmetry. Okay, so, oh dear. It's basically this. But it's a sad face. And so here, now you do it by rows. So now I pick my K horizontally. So somewhere over here, and everywhere below it, I put 0. And then I take the total complex of this thing. So I'll just write down the relevant thing. So you get 2 FK toad C bullet. N, so okay, so you get, so the kth part of this filtration of toad by total complex of sad face. And the nth piece in this total complex is, so again, direct sum p plus q equals n, but now q greater than or equal to k, right? Of CPQ. Similarly, get now E0 PQ2. That's going to be, okay, dot, dot, dot. That's just going to be CQP, okay? Notice I've switched P and Q here. The reason is because when you make this into a spectral sequence, it's just reflecting it across the origin. What? It's flipping it. Like, it turns these horizontal rows into columns. I'm not going to be able to visualize this correctly on the tablet, but it flips it, okay? And so what'll happen is now the D0 are the DH. And so E1 PQ in the second one is just going to be the horizontal cohomology at Q of C bullet P. And then D1 are induced by DB dot dot dot. Yeah. So, okay. I think that's all I have to say. I apologize for being a little quick with the rows, but it is very similar to the columns. So you get two filtrations. The point is that we have these two spectral sequences and they will converge to the same thing, right? Because, I mean, that's what the theorem said earlier. It's just, I had a different filtration. So, okay, we will come to this tomorrow. Thank you. Zoom. Stop recording.